determine the maximum stress induced and the bending moment which will produce the maximum stress. E, that is the modulus of elasticity for a given material which has been given to us as 2 into 10 raised to 5 megapascal. Megapascal is Newton per mm square. Now let us read the data carefully and see what are the things which has been given to us. So first of all, a steel plate and its dimension which has been given to us, that is of width of plate 120 mm and the thickness of plate, that is T, 20 mm has been given to us. Next, the radius of curvature R is also given to us 10 meter, and if we convert it in terms of millimeter, 10 into 1000, 10,000 millimeter is the radius of curvature. Modulus of elasticity, yes, obviously 2 into 10 raised to 5 Newton per mm square, which has been given to us. Now, what is the question which has been asked to us to determine? Question is to find out the maximum bending stress, that is the F max, and the bending moment, the value m, in this particular case has been asked to us. Now, what is the basic particular equation that we have to use? That is F max is equal to E by R into Y max. That is the specifically this is to be known as the bending equation. That is F by Y is equal to E over R. We also told that E by R is a constant term for a given material. Then F is directly proportional to the Y. So, at which case we got the value of F max? We got the value of F max when the Y is equal to Y max. So, here F max is equal to E by R into Y max. So, what is the value of Y max? It is for a rectangular section, thickness by 2, 20 by 2, that is 10 mm. Now, so if we put the value, E value 2 into 10 raised to 5, divide by value of R in terms of millimeter 10,000, multiply by Y max, that is of 20 by 2, that is the 10 mm, we got F max is equal to 200 megapascal. So we got the value F max is 200 megapascal. So also we know that m over I is equal to F max by Y max. We know the value of F max, we know the Y max, we know the value of I. Indirectly the rectangular section has been given to us. We can easily find out the value of m. Now, what is the value of I? For a rectangular section, I is nothing but bt cube by 12. So B, which is given to us 120, thickness is given to us 20, and using our calculator we can easily find out the value of I as 8 into 10 raised to 4 millimeter raised to 4. By putting all the values, that is the value of I, Y and F, we got the value of m by using the simple equation m over I is equal to F over Y as 1.6 kilonewton into meter. So, please check it out, this answer with the help of your calculator. Now, let us go with the next problem. Calculate the maximum bending stress induced in a cast iron pipe of external diameter of 40 mm, internal diameter 20 mm and a length of 4 meter when pipe is supported at its ends and carries a point load of 80 kilonewton at the center. Very interesting question which has been asked to us. Refer the data first of all, and then based on that we can plot this particular figure. Question is that a cast iron hollow circular pipe which has been given to us with the external diameter is of 40 mm while internal diameter is of 20 mm. The length of the pipe is also given to us as 4 meter. This pipe is supported at its two ends, means simply supported pipe is there. Also, it carries a point load at the center of 80 Newton. Only 80 Newton load at the center is applied. The question which has been asked is about calculation of maximum bending stress induced. Now, given data, it is clear to us that is the capital D, small d, length and point load W. This much things has been given to us. Question is asking about F max. We have a very simple and single equation. M over I is equal to F over Y is equal to E over R. 6 terms are there. Only in this case we have to find out F value, that is of maximum value we have to find out. How to find out? Because no direct data has been given to us, but everything which has been given to us as indirect value. Now refer the equation M over I is equal to F over Y is equal to E over R. Then R and E are not given to us. So we cannot use the equation E over R at all in this case. We can use a simple equation, that is M over I is equal to F over Y. Now M over I is equal to F over Y if we can use, then we know that the maximum bending stress is possible when Y is equal to Y maximum. That is, maximum bending stress occurs at the top fibers or at the bottom fibers. So Y max is nothing but capital D by 2. Now what is the value of I? Value of I for a hollow circular section is pi by 64 bracket capital D raised to 4 minus small d raised to 4. Very fine. So we can also find out the value of I. So M over I is equal to F over Y. We found out the two terms. The first term, that is the Y max, we found out the I. Now the remaining term, that is M, that is not directly given to us, which has been given to us indirectly. Maximum bending stress is possible under the maximum bending moment. Recall your fundamentals of the concept of the bending moment. Simply supported beam with a point load at the center, what is the value of maximum bending moment? The answer is WL by 4. So now if we come to the tabletop, then please refer this one. Simply supported beam with center point load W L is the length of beam, then M is equal to, maximum is equal to WL by 4. We should know this one. If you unable to know, then you have to find out reaction first, as it is symmetrical, W by 2, W by 2. You have to find out moment at center, that is nothing but W by 2 into L by 2, that is WL by 4. The same thing we can achieve over here. So now let us come to our problem. The maximum bending stress in a section where the bending moment is maximum, that we have discussed. So M over I is equal to F over Y. F max is equal to M multiplied by I by Y max. For a simply supported beam with point load at the center, the maximum bending moment which is acting at the center of beam. So maximum bending moment M is equal to WL by 4. By putting the value 80 Newton multiplied by L 4000 millimeter by 4, we got the value of moment in terms of Newton and mm. Now moment of inertia we can found out as, this is not Z, this is the value of I, pi by 64 d raised to 4 minus d raised to 4. We know both the values, small d and capital D. We can find out these values, and we can also find out the Y max as d by 2, that is of 40 by 2, that is of 20 mm. Now putting all these values in this equation, we got, that is F max is equal to, we put the value of M, we can put the value of I by Y max, we can get it out, the value of 13.58 megapascal. This is the value of maximum bending stress that has been developed at the topmost or bottommost layer of a section. So now let us go further with the next problem, number 3. A cantilever beam of length of 2 meter fails when a load of 2 kilonewton is applied at the free end. If the section of the beam is 40 mm by 60 mm, find the stress at failure. Now let us think on this particular problem. Cantilever beam which has been given to us, subjected to a point load of 2 kilonewton at the tip, at the free end. The length of the beam which also given to us as 2 meter. The cross sectional area, the cross sectional dimensions also given to us as 40 mm by 60 mm. Intention is to find out the stress at failure. Same logic, stress at failure using the equation, let us be understood on this table top. This beam which has been given to us, the load which is given to us, length is also given to us, the cross sectional dimension B and D are also given to us. We know the formula M over I is equal to F over Y. The stress at failure that is applicable when m is nothing but m max and y is nothing but y max. Y max is nothing but d by 2 because neutral axis at the center, because it's a rectangular section is given to us. M max is equal to point load is there, cantilever beam is there, W into L. I for rectangular section is known to us, 1 by 12 BD cube. The rest parameter is of to find out the value of F. It's very easy. So now let us go to this PPT. L 2 meter, W 2 kilonewton converted in terms of length parameter in terms of millimeter, load parameter in terms of the Newton, width and depth given to us. Now the stress at failure is the value of the stress when the maximum bending moment will be developed in the section. So we got F max is equal to m by z. So the similar case is there. Please come on to this tabletop. M over I is equal to F over y. Therefore F is equal to m into y by I. What is y by I? We know that z is equal to I by y. So F is equal to m by z. The similar equation we can visualize on this particular PPT. That is F is equal to m by z. So now z is equal to BD square by 6. We got the value. Maximum bending moment for a cantilever beam is at fixed end. So m is equal to W multiplied by L, and we got the value in terms of Newton into mm. By putting the value of m, by putting the value of z, we got the F is equal to 166.67 megapascal. It's nothing but same as Newton per mm square.